Today we're going to look at our last section of homework, Chapter 6, Section 4, last section of official homework, which is centered around the second part of the fundamental theorem of calculus, which allows for the construction of antiderivatives. What we need is a function that's continuous on a closed interval and any value from that closed interval. I spelled C wrong down here. There we go. So if we, with the function defined this way, capital F of x as the definite integral from c to x of f of t dt is an antiderivative of f of x. So this reinforces the notion that integration and differentiation are sort of inverse operations of each other. But more importantly, this allows us to construct an antiderivative using a definite integral. And this is good because we can approximate definite integrals to any degree of accuracy, because all we're doing is calculating area as length times width. And so if we need more decimal places, then we just do more subintervals. So with enough computing power, we can do this to any degree of accuracy. Computing power or just time to do the calculation. And so we can't write a nice, simple formula for the antiderivative, like 1/3 x cubed is the antiderivative of x squared, but we can evaluate the antiderivative wherever we want to any degree of accuracy. And that's just as good, especially in a world where we're so surrounded by such great amounts of computing power. So let's keep this in mind and talk about the homework. One of the things that you start, once we have the construction theorem for antiderivatives, we start learning about functions that don't have nice antiderivatives. And this function is one such function. So if we, as in problem 1, this function is the derivative. So we're saying this is the derivative of f prime. So this, or sorry, we're saying this is f prime of x. And we want to construct an antiderivative. So we want to construct an antiderivative. Oops, I wrote sine. Sine is a well-known function that we can find an antiderivative of. All right. So what we know is that we can construct an antiderivative with the second fundamental theorem of calculus. So we can construct an f of x. We can build the family of functions by saying that the integral from some starting point to x of this function, this will be an antiderivative of this function si of x. We can start our counting anywhere. That is something that we have to concern ourselves with. Since we can start anywhere, this function is continuous for everything that's not 0. Anyway, so sorry, I got distracted by something. I'm glad this is all getting recorded. So we need to, since our initial value f of 0 is equal to 2, it would be good to know that when we define our antiderivative, if we just put a +2 at the end, let's make the antiderivative part be 0 when x is equal to 0, so that we can just tack on a +2 at the end. So if we start our definite integral at 0 and integrate from 0 to x of si of x dx, then this will give us a family of functions with a plus c. And then if we use our initial value to find the plus c, that'll be the integral from 0 to 0 of this function. Call it sine again. I finally figured out what was distracting me. I put the x's in here, and they should be t's. So this part is going to be equal to 0. That's what we get for starting off at 0. So plus c, and so we get the 0 plus c, and we want this to equal 2, and that just says that c can equal 2. So the antiderivative that fits the description, we use the second fundamental theorem to construct the family of functions. And then we just add 2. So when we plug in 0, we get 2. And when we take the derivative, we get the psi function. Any questions? No warning when these things are running out. I mean, you could see through them, but you can't actually see where the tape is at until it's like empty, because they have all this writing blocking it. Not that I was paying attention anyway.
Is that the final answer, or don't we have to sine x over x? Don't we have to get the f of x from that? Wouldn't it be cosine something?
No, we actually can't. That's the funny part about this function. That's the thing about this function. This function does not have an antiderivative. Oh, now I know why. Sorry, this is my bad. Psi x is not this function. The trigonometric integral is not this function. Psi x is the antiderivative. All right, let's pause the video here and talk about more problems.